A very good afternoon from us. You are very welcome to our Platinum webinar, Bringing Inquiry into One's Mathematics Classroom. We would like to offer you speech-to-text live captions so that you can follow the written version of what speakers say. If you are interested in this additional help, go to the Zoom menu at the bottom of your screen, and you will find the closed caption button next to the record button. So then you activate the service and you'll be following the text which will be said by the speakers. So to those who didn't attend our previous webinar, I would like to briefly introduce Platinum. Our Platinum project is a consortium of, can we please advance the slide? A consortium of 8 universities in 7, okay, thank you, in 7 countries. So we have the University of Amsterdam, Loughborough University from UK, University of Agder from Norway, which is coordinating, and my name is Yuri Rogovchenko, and I'm the one who coordinates the project. We have also 2 universities from the Czech Republic, Masaryk University and Brno University of Technology, both located in Brno. And Masaryk University is kindly offering us this technical possibility to come with this webinar to you. We have also Leibniz University in Hanover in Germany, Complutense University of Madrid in Spain, and Boris Grynchenko Kiev University in Ukraine. Our consortium is bringing the network further on, and it grows, so that what we have now is also partners in different parts of the world, including Australia, New Zealand. We have also new partners in Ukraine. We have partners in Spain, Future Learning Lab in Norway, and in particular, Masaryk Center for Research, Innovation, Coordination, and Mathematics Teaching in Norway. So Platinum is concerned with inquiry. This is our main interest. And we would like to concentrate on teaching students with the use of inquiry so that they get better conceptual based understanding of mathematics, which also will be fitting their further studies and their workplace situations. And now I pass my word to Professor Simon Guchow, the founding director of Masaryk, who will be our continuity person leading you through the workshop. Thank you.
Thank you, Yuri. And I start with a few details about the webinar. You will find that you are muted and that your videos are turned off centrally by our colleagues in Masaryk. And also the chat function is disabled for you, so you cannot send messages by the chat function. As you will have noted, the webinar is being recorded along with the speech-to-text captions, and the webinar will be available from the Platinum webpage. The program is also available from the webpage, and that address was given to you, I think, with the email that you received with the confirming your registration. Just a brief outline of the program. We start with 20 minutes, 2 short presentations by Professor Barbara Jaworski and Andrzej Heck on inquiry-based tasks. Then the major part of the workshop, the webinar today, will be a workshop by Professor John Mason. There will be a short 10 minutes of reflections on the workshop, followed by another brief presentation by John, a panel discussion towards the end, and then Yuri will end off the webinar for 6 o'clock. There will be an opportunity to set questions for the panel and for the reflections if you want to, and the web address for sending the questions will be available in the chat function. You can just click on that to submit any questions. And there will also be an opportunity there to pose reflections about the group work that you will have during John's session. So that's the arrangements, and it's now my pleasure to start off the webinar properly with introducing Professor Barbara Jaworski, who is the scientific director of Platinum, and Barbara will be followed immediately by Andre Heck from the University of Amsterdam, and they will be talking about designing inquiry-based tasks. Barbara, over to you.
Thank you very much, Simon. I'm just trying to access my first slide, which doesn't seem to be coming up. Can anybody help me with that? Here we go. Very good, thank you. It's my pleasure to talk to you again about our Platinum project, and our focus for this session and most of the webinar is inquiry-based tasks and teaching units. In our previous webinar, which is still available for you on our website, I introduced the inquiry-based activity of our project. And I talked about the model on which our project is based. It's a model of inquiry in 3 layers. And for those of you who weren't here for the last time, I'll just go through it very briefly again. So the first layer is inquiry in mathematics in the classroom, or the lecture, tutorial, workshop, or whatever setting we have for working with our students. The second layer is inquiry between teachers. That is, teachers exploring, learning about mathematics teaching through inquiring into how we work with students in inquiry ways. And, our third layer is what we call developmental research inquiry. This is when we engage in inquiry with our students, collecting data from that activity, analyzing that data, and developing knowledge and practice that we can share with people beyond our project. And you can see this model in 3 layers. And the inquiry is not just restricted to any one layer. So if we're working in the second layer, we might be focusing our development on the activity in the middle layer, the center, or if we're working in the outer layer, we might be focusing our activity on either of the 2 inner layers, collecting the data for analysis and developing knowledge. Excuse me, I'm a bit croaky. So let's move on to what this is about, inquiry-based mathematical tasks and teaching units. This is a major part of our project. We're talking here about tasks which we design, we teachers, because all of us in the project are teachers of mathematics, using inquiry-based tasks with students and designing those tasks. Our aim is to use the task that we design in a teaching session, which can be a lecture or a tutorial or seminar or whatever. And the whole lecture or part of lecture is what we call the teaching unit, which is encompassing on the teaching task that we've designed. So the teaching unit fits around the task or tasks that we've designed. As teachers, we inquire into the design and use of the task. So how well does it work? How do the students respond to it? Does it achieve what we hoped it was going to achieve? We engage our students in using the task, and we reflect on that process. Are there ways to improve what happens? How do the students really use the inquiry role to gain an understanding of mathematics? And so the students inquire into mathematics as they work on the task. So you've seen the model in outline. How does all of that fit into the model? So we have a task designed by the teacher. This is fitting into the second layer. The task is used by the teacher in a session with students. This is relating to the center layer. Students engage with inquiry in mathematics using the task. Again, we're in the center. The teacher observes what happens with the students and reflects on that, and possibly as a result of that, refines the task. We hope that by engaging in inquiry ways with the task, that students develop mathematical understanding. The teacher collects data and analyzes outcomes from working with students on the task. And after analyzing that data, the teacher shares with others what have been learned through that inquiry. So this is our model in practice. So in here, we see two cycles of inquiry, inquiry in teaching and inquiry in learning. The inquiry in teaching involves cycles of activity through designing the task, using it with students, observing and reflecting, and then going back and refining the task in order to use it again. And we collect and analyze data, excuse me, and we disseminate. Here, the students engage with the inquiry-based task. They discuss with their colleagues, specialize and generalize, make conjectures, and convince others. And I hope John's going to refer to all of that in his talk. That leads to proving the conjecture, if that's possible, and reflecting, the students reflecting on what they've learned. So finally, these are the intellectual outputs that the Erasmus project requires. And you can see that IO3 is here right in the center. It relates to IO2, which is on communities of inquiry, and IO4, which is on teaching development. And I'm now handing over to Andre, who will take this further.
Okay, thank you, Barbara. I'm waiting also for getting the control. Yes, so I will continue talking about the three-layer model of inquiry, but then in the context of the design of inquiry-based tasks, which is an intellectual output, the number 3. But first, I want to summarize what we promised in our project plan, and that's the creation of teaching units in a community of inquiry and teaching units that promote conceptual learning through an inquiry approach. And we also promised to blend digital tools and other resources to support lecturers, and in this way also indirectly support students. We would use the teaching units in classroom, in regular courses, and collect data about it. And we also would try to make our units accessible for students with special needs. So you think of students with visual impairness or hearing problems or mental problems. And we would not only create tasks, but also do inquiry about their use. And so we would documentate our work, and the tasks and the documents would be placed in a repository, and we would spread the word about inquiry-based learning, especially in a book, and that book will appear at the end of this year. So what I will do in my part is exemplify this with the work done at the University of Amsterdam, where we not only created tasks or task sequences, but actually had the opportunity to design a completely new module for first-year biomedical science students, basic mathematics. And we organized our community of inquiry around this module. And this community of inquiry consists of the lecturers, the 2 lecturers, the 4 student lecturers working in tutorials, and 1 critical friend. And I would like to mention specifically that we had 3 student lecturers who were biomedical science students, bachelor students in the 2nd and 3rd year, who had taken part in the first versions of this module. And the goal that we set ourselves in this module was to improve the mathematical component of students' biomedical scientific literacy. And we plan to do that by developing teaching of dynamical systems in the context of biological processes. Now that's a long sentence, but if you want to summarize, it's an introduction to systems biology and systems medicine for biomedical students. There are about 150 students per year participating, and they have differing mathematics backgrounds, so that makes a challenge. And currently it's a course which takes 8 weeks. It's in each lesson week we have 1 2-hour lecture and 2 2-hour tutorials. And we not only teach, but we collect data. We do that because of the large size of students with questionnaires, mainly questionnaires about personal data of students or their math anxiety level, test anxiety, motivation and engagement. We have module evaluations, our own evaluation questionnaires and the questionnaires from the faculty, at classroom observations and lecturers' experiences in class in the form of narratives, but also in terms of voice recordings and notes that were taken during the weekly meetings of the community of inquiry. And in these meetings, we formed a common vision on inquiry-based mathematics education. We planned the module, designed tasks, and discussed the classroom experiences, because we didn't have time to develop this module in advance, but actually it was a deliberate choice as well, because then we could develop it while the course was running and making just-in-time adjustments. So the contents is clear now: systems biology and systems medicine for biomedical students. We focus on quantitative mathematical modeling using ICT. And we design activities where students learn the mathematics and learn to explore mathematical models via ICT tools, with the goal to come to grips with biomedical phenomena. And for that purpose, we let students interpret real data coming from empirical research, from research papers. And the reason for that is actually that our vision on IBME is actually focusing on letting students work as much as possible in a way similar to how mathematicians and scientists would work, in particular biomedical scientists. So what kind of IBME elements for lectures and tutorials do we use? Well, they are all focusing on increasing the engagement of students in lectures and tutorials. And we do that by offering tasks in which students can express their own ideas, can work in small groups to inquire into a mathematical concept, to try to understand it more deeply, or to inquire into a mathematical method. And for the purpose of dynamical systems, we also developed worksheets to support this. And here you see on the right-hand screen a worksheet which the students do with pencil and paper, studying a direction field and getting an idea of how you can learn from this phase portrait and sketch more solution curves, and in this way get an idea about the behavior of solutions. Now in Corona times, when online teaching came, we also have digitized all these worksheets. And for that, we used GeoGebra as a basic tool. But we also have JavaScript simulations in our tasks where students have opportunities to visually explore situations, but also explore, for example, neural models that are expressed in differential equations. And since we want our students to act as biomedical scientists and do inquiry in the same way, well, the practitioners will use simulations and program these themselves, probably in R or MATLAB. And so we want our students to program in R as well. And here you see a screenshot which should convince you that the students really have to write their own R scripts, no templates or whatever. And this is a screenshot from an MS Teams meeting where students were working on the R scripts and asked some help from the lecturers. And as you can see from the faces on the bottom line, this was a friendly conversation. These were quite good achieving students. So, but what did we have in mind with all these elements of inquiry? It's to promote the student thinking and reflection. And in the task, we try to achieve this by rephrasing existing questions that you would normally ask, but also extend them. And so many of the questions were having extra questions like why, explain your reasoning, motivate your answer, etc. We also pay much more attention in our tasks to the mathematical methods, but also the mathematics that underpins these methods and the representations that are used for that purpose. And we give a higher priority to reasoning of students and argumentation and giving evidence. And we do that especially by letting students work on the same problem in different ways, using alternative methods that they can come up themselves, that they can propose, and then explore what works best and under what conditions. Well, we also have this outer layer in the three-layer model where it is about developmental research or design research. Now, as a researcher, you also look, of course, as a community of inquiry into the research literature on inquiry-based mathematics education to get ideas, or on the teaching of ODEs, the ordinary differential equations. Well, I won't go into the teaching of dynamical systems here, but you can read the latest literature review, which appeared 1.5 months ago. And in this literature review, you will find a lot of references to IBME approaches for teaching dynamical systems. Especially, we have had, as a community of inquiry, a close look at the inquiry-oriented differential equations project of Chris Rasmussen and colleagues. But looking at all these IBME approaches doesn't mean that you simply have to adopt one. For example, we learned quite a lot from the IOD project, and by looking at the instructional materials that they have produced, but we didn't adopt, for example, this approach as it was based on realistic mathematics education, and we had some hesitations of using that. Pragmatic reasons, it was a short course, we didn't have enough time, the rooms were unfit for group work, and with 150 students, it's difficult to inquire into their thinking in practice during the tutorials and the lectures. And that's a basic principle used in realistic mathematics education. But nevertheless, you can learn a lot from this. And now I'm desperately trying to find the last transparency. Can someone put the last transparency for me? Because I have 1 minute remaining, maybe. I think so. That's about using ICT. For example, there we share with the IOD project that we have a less or more principle. And if I had the transparency in front of me, I could have shown you how we applied universal design for learning principles to help students with special needs. So thank you for listening, and I give over to Simon again.
Thank you, Andre, and thank you, Barbara, for your two brief presentations. It is now my great pleasure to introduce and welcome John Mason, who will lead our workshop workshop from this point on. Actually, worship is not a bad word to use, given that we're dealing with mathematics. John has got many years of experience leading workshops to challenge teachers at all levels to think mathematically through inquiry-based tasks and activities. John is Professor Emeritus at the Open University in the UK. Thank you, John. Over to you.
Thank you, Simon. And it's a real pleasure to be here and to take the impulse of your invitation to work on some of these ideas. Can we stop the sharing from the center, or do I just share? Oh, all right. I can just do it. Good. Okay. So, bringing inquiry into my classroom. Yep. So the focus for today, my concern is always with the lived experience of learners of mathematics. And the best way I have found to access that is to start with inspecting my own experience. So my invitation to you today is to inspect your own experience and so that you can use that to inform your actions in the future. So to this end, I'm going to offer you some mathematical phenomena, some situations in which something happens or fails to happen, and which therefore opens possibilities for exploration, leading to enriched comprehension of concepts. I hope that makes sense, and I hope it'll make much more sense when I get into my first example. Or situations intended to provide immediate experience from which to learn about problem posing, about exploration, and about mathematical thinking, or indeed about mathematical concepts. My interest today is particularly in how questions worthy of exploration actually arise, where do they come from, why some might be chosen to use with learners, and most specifically, pedagogical actions which promote exploration and which provoke mathematical thinking. For me, it's absolutely essential to establish what I call a conjecturing atmosphere, and I'm going to rehearse some of this now to remind you about how to behave in the breakout groups where I invite you to work on a task for a period of time. So for me, conjecturing is the essence and the heart of mathematical thinking. Mathematical thinking can only thrive in an atmosphere of conjecturing. So that means that everything said today, especially by me, is to be treated as a conjecture. It's said with the intention to modify it as and when necessary. So you mustn't believe anything that I say. It must be tested in your experience. So, for example, nothing said in a conjecturing atmosphere is deemed as wrong, but rather it may be in need of modification. And although it's a euphemism, it makes a big difference in the atmosphere and the ethos of the classroom if you get away from right and wrong answers and into an interesting conjecture, but it might need modifying. In a conjecturing atmosphere, those who think they know listen attentively and perhaps ask questions or offer examples which challenge or indicate useful foci of attention. Those who think they do not know take opportunities to try to express their thinking and their uncertainties. And so a community of inquiry develops where people are supporting each other. So I've got to make some assumptions. I've made some assumptions in preparing this. I'm well aware that many of you are teaching people for whom mathematics is at best a tool. They want to internalize the tool and get on with their own subject. However, in order to use mathematical tools appropriately, it's extremely valuable to learn how to question and probe mathematical phenomena. I assume that everyone has innate curiosity that can be brought to the surface. That bringing to the surface often depends on a relationship of trust with between the teacher and the students trusting the teacher that they will ask something that's approachable and doable, and the teacher trusting the students that they will engage. I assume that every mathematical concept, this is a conjecture really, technique or tool, has at its heart one or more mathematical phenomena. And so I'm going to begin with my first task. So ride and tie has a context. In the 18th and 19th centuries, people who did not have access to their own horses would sometimes journey together, sharing a single horse. So what would they do? One would walk and the other would ride. Then the rider would tie the horse somewhere, on the path obviously, and walk on, while the walker, when they arrive at the horse, mounts the horse and rides on past the walker, before tying the horse and walking on. And of course the aim was to adjust their trip so that they arrived at the destination at the same time, while also allowing the horse suitable time resting between riders. Now, not many people I've come across have actually heard of this idea of ride and tie. So historically, let me just tell you that in 1742, Henry Fielding mentions ride and tie as a means of travel often used. And I came across somewhere a statement that two people, they gave me the names, I've forgotten them, two people crossed the Adirondacks, a mountain range in the east coast of the United States, using ride and tie in order to attend Harvard as undergraduates together. One of the two became president of the United States, and the other became president of Harvard. And there are still competitions going on in North America, which involve complex extra rules involving ride and tie. And finally, there are two problems by Polya in his mathematical discovery that essentially are involved with ride and tie, but they don't use horses. So that's the context. Here's the task. I'm going to display a graph of distance against time. But before doing anything else, when you look at it, I want to invite you to say what you see to yourself, obviously. If we were doing this live, I would have you doing it in pairs. The point about say what you see is to pick out various details that catch your attention before you try to develop some story about what's going on. Then I would like you to look at the graph and see what you think about it. So here's the graph. I'm hoping that your attention has gone over to the left, where there are two blue vectors. One is the speed that A rides at, the other one is the speed that A walks at, and two green ones for B riding and B walking. I hope you can see that there's a graph, and it seems to be plotting what A and B are doing. So I've got an animation here showing that you can, in the applet that this comes from, you can adjust the speeds. And if you look here at the top right, there's a gap that they don't end up arriving at the distance at the same time. And if we follow the track of the A rider, the A walker, A person, they rode, then they walked, then they try to ride again. But there's a problem here, because they need to only arrive and pick up the horse when the horses got past them. And so in the animation, you can see that there's now a solution to the adjustment of how A and B go. Now, the point about say what you see is to get people to pick out various details before enacting any other action. I'm willing to conjecture that some of you have students who, as soon as an action becomes available to them, they immediately enact it before really thinking about the problem. And I find the slogan, say what you see, really useful for slowing people down and getting them to think before they act. Now, why might I use this simple task? Well, I've used it with hundreds of people in many different countries. And one of the reasons is that it is a common experience that many students think that drawing a graph is the end of a task. It's the end, it's the result of a process. And that once you've drawn the graph, then you go on and do something else. And I want to emphasize that the drawing of the graph is in order to then read it, in order to interpret, in order to draw conclusions from it. I also use it because I notice people jumping in, or indeed, another phenomenon I've noticed is that people see a graph in a textbook and they sort of gaze at it, but don't analyze it and just assume that it is showing them what the text is telling them it's showing them. And it seems to me that's a really useful thing to learn to do, to interrogate representations, to make sure that they're displaying what they intend to display. Right, that gives you a taste of the way I work, and so we'll move on to another task. I want to define the notion of tangent power of a point P with respect to a function f is the number of tangents to f that pass through P. And so the question I ask is, what is the tangent power of P with respect to this particular quintic? Well, I think it's interesting to notice how one actually does it. How did you imagine doing the counting? For example, you might have set a line through P, or imagined it, or even produced, did one physically with your finger or a pencil or pen or something. And you could rotate the line about P and do the counting. But you could also run a tangent along the curve and see how many times it goes through P. Now, I'd like to illustrate for you, give you experience of using polling with Zoom when you're teaching at a distance. And so I'm going to ask you some questions, and we're going to set a poll. We're going to invite you to respond to them and see what sort of responses we get. So my first question is, did you first think of rotating a line about P as in the left animation? Or did you first think of running a tangent along the line? In question 2, did you actually count, or did you actually not really engage? And question 3, if you did count, did you use a physical object like a finger or a pencil or a pen, or did you imagine a line doing things? We seem to have become static now. Whoops. How do we do? Now that is very close to what I conjectured would happen. That the first action that occurs to me, namely rotating a line about the point P, a line that goes through P, but rotating it about P, is an obvious thing to do because that's what the definition seems to indicate, and so I immediately do it. But if you stop and think about it for a minute, running a tangent along the curve actually has some major advantages. So this is for me an example of how I can use a task to remind students that stopping and thinking first before acting is really a sensible thing to do. Good. How do I finish? Get rid of the poll. Right. So the question that seems to me to be absolutely shouting at me is, what happens if I move P? So what are the possible tangent powers of points with respect to the quintic? Now, if you were working in a workshop with me physically, then I would leave you to do some thinking about it and some working on it. But because we're not in that situation, I'm going to show you an animation. I just need to work out how to do that. Oh, is that what I wanted? Oh, yes. Okay. So there we go. To me, there's an active, a physical sense of what inflection points are about, whether the tangent changes direction. That's manifested in the count. You may notice some curious things happening. So for me, that's an example of a mathematical phenomenon. When I first saw this a long time ago now, I wasn't expecting that the tangent powers would change by 2 whenever you crossed an inflection line. So I had some explaining to do, which I worked on. Good. But that raises, so doing it physically provides that inactive sense, where previously for me, the second derivative was simply a thing you computed and put equal to 0 and mucked around with. So this is a way of enhancing my sense of what the second derivative is about. Combining it with the Taylor series, to me, raises even more questions. So if I think of a tangent as a first-degree Taylor approximation, then I've got a more general phenomenon. Here comes the second-order Taylor approximation. How many of them go through P? And so my definition of tangent power becomes a definition of Taylor power. So the Taylor power of P of degree 2 is in fact just 1. Only one of them actually goes through P. Oh, and here we have the analog to inflection points. It's when the second degree Taylor approximation changes direction. So now I'm beginning to see inflection points as part of I'm seeing in a broader context, in a wider context. They're starting to make more sense to me now. And here's the Taylor approximation of degree 3. One of them went through P. Then it changes direction. And so the Taylor power of degree 3 for this quintic, excuse me, is just 1. So I'd like to pause there for a moment and ask you simply to think to yourself, what struck you mathematically? What struck you pedagogically And can you tell yourself a story about what was going on in the last animation? And give you a short period of time to do that for yourself. Obviously, it'd be better if you were doing it in pairs, but we haven't got that luxury. So what I'm doing here, I'm obviously, I'm anticipating that many of you will know precisely what's going on, but I'm trying to illustrate pedagogical moves, inviting people to consider what struck them mathematically, and over a period of time, I would develop a vocabulary with them for what we mean by what struck you mathematically. Opportunities to specialize, to generalize, to make conjectures, to convince, and so on. But also what struck you pedagogically. Now, we're not going to ask students what struck them pedagogically, perhaps, but I'm going to have related questions to that about where might they use this, or what other constructs that they've met, concepts that they've met, are related to what it is they're seeing in the current phenomenon. And this business of telling yourself a story about what was going on, constructing a personal narrative, I've become even more convinced than I was already many years ago, but most recently, that a significant contribution to learning comes about by constructing a personal narrative. It doesn't want to be, and it doesn't have to be, in fact, it mustn't be the narrative which is written in the textbook or given by the lecturer. It's the one that's personally constructed by the learners. And of course, that personal narrative may have some infelicities, some inappropriatenesses in it. But that narrative will develop and modify over time until it settles down to being a reasonable narrative. And I don't need to be present and to check everybody's narrative at every stage. That's a process that I put trust in the learner about. Now, thinking about the Taylor powers, what about the zeroth Taylor power? Looking at P, you can tell me immediately, if you were able to, you can tell yourself immediately, what is the zeroth Taylor power of P? The zeroth Taylor power is simply a horizontal straight line. So how many horizontal straight lines go through P? Obviously 3. And how is that Taylor power going to vary as P moves? Well, those are the regions. The regions correspond to the turning points of the function. So that, for me, puts maximum and minimum, local extrema. That puts it all in a new context, a wider context. And for me, that makes me feel as though my appreciation has been enriched. Okay, I'm slightly ahead of time, which is fantastic. I'm going to suggest we have a break for 5 minutes. So I'm going to start again at in 5 minutes' time, which I make to be 5 to 4 your time. 5 to 3 my time, but 5 to 4 your time. That's 6 minutes. So we'll take a break, stretch your legs, have a think about what's happened so far.
Thank you, John. See you back in 5 minutes.
Yep. So one of the questions, just before we have a reflection period, one of the questions that I find comes up with this task is people suddenly say, what about sine x? And so I've got sine x ready to show you. Share. Now, I gather that we have at least one person with us whose sight is not perfect. And so I'm going to describe what's here. At the top of the slide, it says, through what angles can the graph of sine of x be rotated and still preserve the property of being the graph of a function? So the animation shows a green copy of sine x, and there's a point x on the x-axis and the corresponding point on the graph of sine x. So I'm going to rotate the graph of sine x, or at least the animation is going to. It's rotating it counterclockwise through, well, through an angle of 45 degrees. Now there's a tangent at the point corresponding to x on the x-axis on both the original graph and the rotated graph. And it's showing that the tangent to the rotated graph is sometimes horizontal and sometimes vertical. So if you wanted the resulting function to be differentiable, this sine x wouldn't do if you rotated through 45 degrees. But if you divide by something bigger than 1, in this case it's showing sine x of divided by, well, it was 1.32. When you divide by something smaller than 1, it's no longer a function. But when it's bigger than 1, not only is the graph of the rotated graph of sine x a function, but it has some interesting properties. And so one of the questions to be asked whenever you have a construction device available to you is to ask, what other properties does it have, and how might that construction be useful in the future? And it turns out that I was playing with this at the same time that somebody asked for a differentiable function with infinitely many fixed points. And it occurred to me that what you can do is take one period of the rotated graph. It crosses y equals x at 3 points. So you take it at between the endpoints. And now you can scale that and glue it together on lots and lots of smaller and smaller and smaller intervals. And you can produce some pretty weird functions. So the point here is that by asking a question, I end up with a construction of the device that I could use to create more examples for myself. And the feature of these examples is that most of them cannot be given by elementary functions. So I'm going to suggest we have a little break now, during which you can reflect, and you can offer your reflections by going to the link that's in the chat, where you're invited to distinguish between reflections and panel. What struck you mathematically? What mathematical ideas did the task bring to the fore? What aspects of mathematical thinking did you notice? I've listed a few: imagining and expressing, specializing and generalizing, conjecturing and convincing, characterizing and classifying, and room for lots more if you have them. The most important thing is, what did you notice about opportunities to make choices and to explore? So we now have a period of time when you're invited to put things in the chat. Use the chat link to put things in reflections.
Right, I'm now going to invite members of the Platinum team to pick up reflections that have been written onto Padlet, or bring their own reflections on their experiences of the group session that John has just set up. So it is now over to the Platinum team, who I hope are going to join in at this point. Thank you.
Right. So I joined one of those groups where the numbers were very low, and we had a lot of fun. And as I already confessed, we failed to meet John's expectation, coming up with a good conjecture. But what I really noticed, and this is what I also left in the comments, is that we very badly needed your animation tools to be efficient in answering your questions, because it looks like if we are facilitated with your applet, we can really do a lot of nice work in a very limited time. Otherwise, we were playing with this Word document and it was not the most efficient thing, but we have got some rough ideas for the most simplistic case, like playing with the X square graph. We came up with a conjecture, which is like about 10 degrees rotation would be still fine, but that's as far as we could go. Thank you.
May I? Oh,
yes.
Andre.
Okay.
Go ahead, Andre.
I joined another group and experienced what I had foreseen, that we had a silent group, but they were working all on their cells, trying to figure out what in the handouts was written and what we were supposed to do. But once one person starts asking a question, then the discussion blows up. And we haven't gotten further than rotation because that was already complicated enough for us. And I think I added to the discussion a point of view which made it even more complicated, because of my physics background. I was thinking in rotation about active and passive rotation. So I was thinking about rotating the coordinate systems. And that helped us a bit in the discussion, because in this way we could easily see that symmetries for the coordinate system, that obviously doesn't change the function property. So for example, 0 degree rotation and 180 degrees rotation always will do it. But then we had a difficulty with the 3rd degree, because then it depends a bit on what the graph looks like. So we didn't get further than that. And that, I think we also needed some exploration tools. But the other option that we looked at was trying to figure out what was the criterion for a function and this vertical line argument. So I'll leave it to this and give the word to Barbara.
Thank you. Sorry, I was muted. Yes, well, I was in just a small group. There were 3 of us there, and we started off thinking about the graphs. But like Yuri, we didn't, because we didn't have the ability to animate them, it was difficult to visualize. And so it just shows us the power of visualization, because as soon as you can start to rotate something, you can be clearer as to what's actually happening to it. But one of the things in our group was that we are all teachers. And you know what teachers do as soon as they start to look at something like this, they think about how they might work on it with their students. And so we got into talking about what we might do as teachers if we were going to try to get our students involved in such a task. So that was, well, certainly it was very interesting for me. I think it was, sorry. I think it was for the others as well. I'll stop there.
Gosh, I hope you're all right, Barbara.
Marienka?
Okay, thank you. I have a comment from different perspective. We as teachers, usually when we pose some questions or bring some tasks for students, we usually know the answer in advance. Usually we are teaching what we know. And for me, it was nice experience to face a problem where the solution was not obvious for me as a teacher. And after 15 minutes of discussion, we didn't come to a conclusion what's the proper answer. So we could have the same experience like students have when they start to study something what is new for them. But the teacher usually for teacher, it's not easy to imagine how the students feel when they start to completely new thing. So this was a benefit for me to experience how the students feel when they don't know at the beginning anything. And the second thing, what comes to my mind is that students usually give tasks where they can compare some rules, formulas, developed ideas with the task they get. And now it was really very open, with no direction what to do, no hints, no similar tasks they went through already, so they can compare how did I do it first time, now it could be similar. So it was really opening just questions. So that was also interesting for me. So that's it, what I wanted to say as my reflection on this. And thank you to all ladies. I met some of them from Mexico, so it's nice to speak with someone from Mexico when I am located in Czech Republic. So I wave.
Lukáš?
I'm sorry, Josef. I just only let you inform that I try to copy and paste the reflections from participants from Padlet, so you can see them in front of you. A lot of them are to John, so we may postpone them to John and let it to the panel. My own reflection is very poor because I was occupied by technical issues, but what was really needed is that you were not able to share the document with others. And so this was a difficulty for us in the first 5 minutes. So it was solved then. And the other thing is that I met maybe 3 or 4 rooms, and it seems to me that again it was difficult for people who don't know each other to let themselves open and try to conject and try to think out the solution of problem. That was my impression at the first case.
Yeah, okay, so it's time for me to share my reflection, and that should be the last one. So then John will continue. My first observation was that when John announced that there will be a breakout room session, what happened was similar to what we experience with students. If we announce there will be a breakout room session, the students start to disappear. So some don't join the breakout room and stay in the main hall, and some disappear completely. And we could observe the same phenomenon today at the webinar too. That was my first observation. Then I tried to go through all the breakout rooms where someone is, because there was one which was completely empty. And I have noticed that there are different strategies that people try to use when dealing with the tasks. So starting from just imagination and using hands, then using some physical objects like pens, then paper and pencil, and some of the groups also use digital tools. I have noticed GeoGebra. So that was interesting to see the different strategies, how people do it. And some of the groups also discussed the experience of being put in the students' shoes, as Marienka already mentioned. And I think there was one more group there. They discussed sharing experience with teaching and inquiry-based mathematics education and so on. So that this is my reflection. Thank you.
And thank you to the Platinum team. John, you've now got about 30 minutes left for You might want to pick up on some of those reflections, but I think you have another couple of tasks for us to look at. So John, over to you. Thank you.
Right. Thank you, Simon. Thank you for those reflections. I find myself, listening to the reflections, very tempted to try and show you one of the applets actually functioning so that we could investigate it further. But in fact, the point of today is not to learn some mathematics, but to experience the opening up of exploration and the role it might play and how to work with students on it. Excuse me. So I'm going to resist the temptation to get caught up in the mathematics. Someone reported, I wasn't able to get everybody's name, but someone reported that although the exploration, the lack of exploration tools made things difficult, but one of the things that came up was the criteria for something to be a function. And that is precisely what the task was designed to do initially, is to bring to the surface the characterization or the definition of what it means for a graph to be the graph of a function. And it does it by putting the whole question in a context, namely the context of rotating, in this case, rotating a graph. And so for those people, the task was absolutely effective because it brought up the question of what does it mean to be a function. I was interested that people were talking about being able to cope with it on a finite interval, but not sure what happens asymptotically. And again, one of the purposes of the task with the quadratic was to work on this issue of what happens to what does the tangent of the quadratic look like as the point that goes through on the x-axis gets arbitrarily large, either positively or negatively. So as x goes to infinity, what happens to the tangent to the parabola? Well, the parabola gets steeper and steeper and steeper. The tangent, so the slope of the tangent, gets arbitrarily large. If the slope of the tangent is arbitrarily large, if you try to rotate the quadratic through a tiny, tiny angle, all I have to do is to go farther out so that the tangent is actually steeper than that, and it will no longer, it will show you that it's no longer a function. So the quadratic cannot be rotated apart from through 0 and 180, of course. But it cannot be rotated through small angle. And that, for me, is about getting people to appreciate what's happening off the screen. There's a tendency to think that a function, what you see on the screen is all you're getting. And so for me, this task was partly constructed in order to bring that very issue to the surface. In the applet, I've got a vertical line that you can run along so that you can test whether something is a function, at least within the visible domain. And I put that in as a response to people using the applet and wanting to have a test line that they could use to check whether or not a picture really was a function. Somebody asked whether tangent power actually has any applications. And the answer to that is not mathematically, as far as I know. I haven't been able to come up with any. But I think it has an enormous application in bringing to attention the nature of the Taylor approximations. Normally, people talk about the Taylor approximation at a point. And this task tries to open that up and give you a sense of what is it like, how does the Taylor polynomial of any particular degree, how does it change as the point of contact runs along the graph of the function, runs along the curve. And so it seems to me that the task is working quite well in bringing about that awareness. And the whole point of having the tasks fairly open is that I was trying to indicate a domain of investigation, but it's up to the students to learn how to precise that. And that's true for engineering students. It's true for computing students. It's true for social science students. It's true for biomedical students. Everybody needs to know how to make the question precise so that they have a chance of addressing it mathematically. And so it seems to me really important that people experience that in the lectures or the seminar, workshops, tutorials, whatever you call them. Right. I think that's pretty much what I wanted to say. I mean, certainly the experience of breakout rooms, it takes, you know, the first time you found yourself in a breakout room with people you're not familiar with, it takes a while. It takes a brave soul to ask a question or to indicate that they don't know what's going on. And then that tends to open things up and it gets going. But it takes a little time the first few times. But if you establish breakout groups as one of the features that are going to take place let's say, increasingly. So you do it for 10 minutes in one lecture, and then maybe 10 minutes in another, and then maybe 15 minutes in another. Gradually increase the time. People will get used to working in breakout rooms. Right. I'm going to now share my screen and to offer you one more context in which exploring the context which is very familiar. It's fundamental to any use of mathematics, namely vector spaces, and but yet it raises questions. I found myself raising questions that I've never noticed in a textbook before. I'm not claiming that they're important questions. I'm just saying that they're questions which arose for me freshly. So I'm going to show you a series of probably 4 animations, certainly 3, maybe 4. And I'm going to suggest that your task is to try to say what you see happening before you say, oh yes, that's just something or other to do with vector spaces. To try and, as it were, give a running commentary. Now, I'm going to show the animation once, and then I'm going to describe it for our colleague who can't see the screen. So you get two goes at the cherry. So this is the beginning of linear algebra. The reason I'm not describing it immediately is because my description will tell you what's going on. So let's go back and we'll see it again if I can arrange to do that. Okay, so on the screen is 2 basis vectors, one to the right and one vertically. So they're orthogonal, and they're thought of as unit vectors, and they're called E sub 1 and E sub 2. And there's a vector V in blue with an arrowhead, and the beginning of the animation, the V moves around. So I'll start the animation again. So an arrow grabs the V and moves it around. And then there shows up 2 other basis vectors in red, F1 and F2. And they're being moved around to show that they can vary in whatever way you like, pretty much. And then the image of V is called W. So V went to E1, and the W went to F1. When the V is scaled, the W scales. And when the V goes to E2, the W goes to F2. For me, that's an attempt to indicate that I have a linear transformation. V maps to W, and we have W is a red arrow, and it's going to be thought of in terms, we want to know its coordinates in the red basis, F1 and F2, but we know the coordinates of V because it's in the blue basis, E1 and E2. So then on the screen it comes up, tell yourself a story about what you saw happening. And now we go to the next animation. I should describe, okay, now I'm going to run it and then describe it. So tell yourself a story about what you see happening. Now the vector is just moving around. But okay, let's back up. And no, I don't want to on this one. So on the screen is the E1 and E2 basis with a blue vector V and an F1, F2 basis in red, and the image of V under some transformation, the change of basis, is the vector W. So the idea is that the first animation provides a kinesthetic sense of what a matrix does, because when the V vector coincides with E1, the answer is F1, and when V coincides with E2, the answer is F2. So the matrix is performing that transformation, and it's the column vectors. And now what we've got happening, once I get it started, is that we see both of those. Now we see two blue dots corresponding to the coordinates of V in the E1, E2 basis, and then V is moved around, and you can see and now, let me pause it, pause. And now you can see that there are lines joining E1 to F1 and E2 to F2, and parallel lines to those going through the coordinate points for V, the projection of V on E1 and the projection of V on E2. So now we've got red coordinates for V, but we're interested in the coordinates for W, and when that carries on, V is moving around, showing the red coordinate things changing, and now the red coordinates of W are presented. Oh, stop. Linear transformation 1. How did that happen? Now I'm lost. That's where I want to be. But gosh, it's hard to work with this screen. So I've now stabilized it. So the vector V with the blue arrow and its blue coordinates, the vector W, which is a red arrow, and its red coordinates, and the relationship between them is the parallel lines between the lines that are parallel to E2, F2 and E1, F1, and those give the relationship between the coordinates of V and the coordinates of W. Now this picture needs a lot of thought about, but I suggest that the reason some people have difficulty with linear algebra is that they've never actually thought about this diagram. I happen to know that many lecturers, in my experience at the Open University, have come a cropper when they've tried to give a lecture on change of basis for linear transformation, because it requires very careful preparation to make sure you know what's what. And I think I've tracked it back to this diagram is showing the relationship between the coordinates. So again, the invitation, and this is the important part of the pedagogic part of what I'm doing, is to tell yourself a story about what you see happening, or in some cases, what you heard being described as happening. Okay. Now we've got linear transformation 2. So here what we have is a blue vector, which is sitting, it's one end at the origin, the other end is on a circle. Let's say it's x squared plus y squared equals 1, the unit circle. So the blue vector is going to rotate around the origin, staying constant length. So its end is going to stay on a circle. And the red vector, the image vector, is going to be tracked, and it shows up as a dotted curve. Let's see if we can get some of that happening. And it turns out that the blue vector coincides with the red vector at one point. Now suddenly we see something that perhaps I should pause it and back up a little bit. Now what we see is a dashed line joining the tips of the blue and red vectors. So that's the vector and its image. And treating that as a vector, which is purple, there's a purple vector from the origin, which is parallel and of equal length to that. So the purple vector at the origin is tracking the difference between the vector v and the vector w. And there's a point on the blue vector v, which is the same length as the purple vector. So we're going to plot what the length is of the vector of the difference between v and w. Now that's not something that you normally see in textbooks, or whoops, what happened? I don't know. Oh, it's gone on to the, okay. Gosh, it's hard to keep. Okay. So the blue vector is now going around the circle. The red vector is following its path, which is an ellipse, and we see the difference vectors and the plotting of the difference vector. And now we see the track or the trace of the plots of the difference vector and the vector on v, which is the same length as the difference vector. So what I'm doing now is providing the commentary that I was hoping you would be having to do for yourself. But there's more. But I've got to get it to, I don't want it to do that, I want it to do that. Because you can see there's the angle between V and W, between the blue and red, is now black. And the cosine of that angle is also being tracked, and it's green. The value of the cosine of the angle between V and W. And of course, in this instance, the V and the W can overlap at two places, 4 places. So we know it's very tempting to bring in the notion of eigenvectors. So this isn't working quite the way I wanted it to, because I'm having to describe what I'm seeing, but I'm going to, so now I want to show you one more. Well, let me just pause, let me just go back and pause for a moment. So all of this arose because I had access to dynamic geometry, and I wanted to understand what was going on with eigenvectors and eigenvalues, only working in 2 dimensions, of course, but that's what's available to me. But in doing the animation, I find myself asking questions like, well, what's the difference between the red and the blue vector? Ah, it's a vector. Let's plot that vector. What about plotting the magnitude of that vector, but in the v direction? And so I get the two purple curves. And the angle between the two vectors. Maybe that's significant. What's about the cosine? And suddenly I get these other pictures, and so I have questions to ask, like what happens when there is no eigenvector? What's the situation there? So we go on to the next and final animation. And here we see the blue vector on its unit circle, from the origin to the unit circle. We see the image vector, the red one that's dashed. But we also see two red bases, F1 and F2. And, oops, don't do that. Oh yes, it's all right. So the blue vector is traversing its unit circle. The red vector is traversing its ellipse. And now F1 has been moved. It's a different basis vector now. And if you watch the blue and red vectors, they're not going to overlap at any point. So in this particular case, this matrix transformation, there is no eigenvector, eigenvalue. Oop, the red basis has changed again, and now the second F2 has been moved. And for me, one of the questions that this immediately posed for me was, if I fix F2, where can I put F1 and I will find an eigenvector? And where can I put F1 and there won't be an eigenvector? Or in other words, what's the boundary between the regions? The applet does that, but the animation doesn't. Oops. That was unexpected. Carry on with the animation further, I hope. Yeah. So in this case, there are eigenvectors, and one of the questions is, what are the directions of the eigenvectors, and how do they relate to the ellipse that the image vector traces out? Because it's not what you might first anticipate, namely that the eigenvectors are in the axes of the ellipse. Quite the contrary. At the moment we've got it where the bases have been chosen where there's no one. Now there is an eigenvector. The basis vector has been moved. Now there's no one again. So I'm going to stop all of that somehow. I can't remember what happens. Oh yes, it just tracks. It moves the F1 and F2, and it shows you how the cosine of the angle between the vector and its image shows up, and what and so on. All I'm trying to do here is to indicate that. Let's stop it. I'm trying to indicate that when you have access to powerful tools, you find yourself asking questions which are non-standard. Now, I'm not saying that these questions are good ones for students, but I'm saying that they challenge me as lecturer to probe more deeply excuse me, constructs that I thought I had previously understood, comprehended, appreciated. And I find that when I start to explore, my comprehension, and sometimes even my appreciation, deepen and become richer and richer. And so I'm suggesting that it is possible, when working with students, to provide them with situations in which they are encouraged to ask questions, to pose themselves questions, some of which they won't be able to answer. That's fine. That's what mathematics is like. But in the process of exploring, they are enriching their notions of their images, the concept image, the associations that they have with the concept. So what did you see happening in one of the animations? What did you find yourself asking about or wanting to explore? I hope you found yourself asking questions before I did, rather than afterwards. And I was hoping that we would have some time, but I don't think we do. I'll check that in a minute. To ask yourself, can you think of any concepts that you teach which could be introduced and or reviewed by displaying a phenomenon and asking students to make sense of it? So what I'm suggesting here is that you can use a phenomenon such as the animation showing the coordinates of vector and its image under and change of basis. You could use it beforehand to motivate or to indicate what it is that you're going to be talking about and refining. And you can also use the same animation, or the same phenomenon at least, as a revision for students to, now that you've studied this area, you should be able to make sense of this phenomenon. So I'm going to give you a few moments to think of whether there are any concepts that you teach which might be introduced or reviewed by displaying some phenomenon. And it might be that you need to get help from somebody who uses dynamic geometry or Maple or Mathematica or something else to help with that. But the point is that the tool can enrich and extend the kinds of questions you ask, and therefore also the access that students have to appreciating and comprehending the basic concepts that you're trying to teach. So I'll shut up for a minute. Okay, I'm hoping that you treated this last one, in fact all of the animations that I've shown, as me being playful, and hence playful, emphasizing the playfulness. So many students see mathematics as a burden, a collection of tools that they've got to accumulate and know how to use, but without actually appreciating, or even in some cases comprehending, what those tools do and what they don't do, more particularly. And encouraging a playful attitude to posing mathematical questions seems to me to be a valuable attribute for all classrooms, including students who are engineering or computing or some other discipline who aren't initially all that interested in the mathematics, to appreciate the underlying concepts and the tools that they're approaching or trying to acquire. To appreciate and to comprehend those really requires some time to explore. That's my line, and I'm going to stick with it. So I want to come back to say what you see. When you first meet a diagram or an exercise, a set of exercises that you've been given, a problem set, it can be very helpful to first say what you see, using only language familiar to everyone in the group. No prize for being clever, sticking to details that catch your attention. It's a really good way to prepare yourself before you dive in to some action which has come to mind. And as I think was shown, your first conjecture isn't always the best one and may need modifying. The first action that becomes available isn't always the most appropriate one. So say what you see is a nice little slogan for reminding myself to stop and think. As a study strategy, and even as an exam strategy, say what see enables you to pause and consider possibilities rather than diving in and carrying out the first action that becomes available. Inviting learners to tell a story about what they see or what they saw happening. Basically constructing your own personal narrative, PN for short, which makes a big contribution to your concept image. by using say what you see and personal narrative in class as pedagogic actions to initiate, and at some point drawing attention to them explicitly, you can help learners integrate them into their own functioning so that they do them for themselves when they're studying. So, what is your uppermost concern now? You can pose questions to the panel and you can offer your reflections. Again, that link is in the chat, or will be if it isn't there already. And that's all I want to present to you today. I look forward to trying to engage with some of your questions.
John, thank you very much. As always, I've experienced your presentation as challenging, extremely challenging, deeply informative, very interesting, but most of all enjoyable. So it was a good time of worship. Thank you. And now it's my pleasure to hand over to my colleague, Professor Thomas Yesterland, who is the current director of Masaryk, and he will lead the panel discussion. So over to you, Thomas.
Thank you, Simon. And we're going to welcome some panelists for a discussion. John, you will be joining the panel, and we will also have Barbara and Andre, who spoke earlier today, can both be with us. And also we have Maria Kralova, do I pronounce it correctly? Maria Kralova, yeah, okay. From the Masaryk University, and and she is the head of the department for the Department of Applied Mathematics and Computer Science. So we are going to have some discussions about some of these questions, and we have some questions prepared already. But first we have one question which goes to you, John, which came in the Padlet. So you see a lot of math in all this, your graph and all your dynamic tools. Do the students see it immediately? Do the students find it, or do they need a lot of guidance in order to start figuring out the math in those problems you give them? You have to unmute yourself, John, if you are now muted.
Thank you. Of course they need help to start with. I dropped people who were here today into it because I recognize them as experienced teachers. If I'm working with a class and I don't know the class, I would start with, say, what you see, for example, with the ride and tie. It's a beautiful example of a situation where you invite people in plenary to say, or to say in pairs to each other, what do you see on the screen? And then to ask them to speak to the teacher, in other words, in plenary, to offer up things that they saw. And you, by working on that way, in that way for a short period of time, in several successive sessions, you will begin to, the students will begin to pick up that it doesn't hurt to offer something. The worst that can happen is that somebody's going to say, maybe you want to modify your conjecture, or I would like to modify your conjecture, or how would you take account of this example, and so on. Nobody's going to be put down in any way, shape, or form. And in my experience is that people respond to this very quickly. I mean, for example, with the reading of graphs, that's a particular bête noire of mine, because I think that I suspect that a lot of people, a lot of students, don't get to interpret graphs. They simply draw graphs or sketch graphs. And so I look for, it seems to me, where I detect a possible weakness, I want to construct a task which will plunge people into that and give them opportunity to work at it. So, of course, people need support and introduction. I was concerned today that there would be experts who would know everything that I was talking about. And so that's why I offered, I mean, you know, things like I I have not yet myself articulated which shears are actually acceptable to preserve a graph as the graph of a function. I have a taste of the answer, I have a sense of it, but I've not articulated it. But I have done some of the other ones. That's fine. So, yeah.
Yeah, thank you. And it's playful. You know, it's fun to play with. I guess that's get them started and to see the problems.
I think that's really important. Yeah.
And it's easy to start. So thank you. We're going to move on with the first question now. And the question would start about inquiry-based problems. If I could make, let me see if I can change the slides there. Yeah, thank you. The first question to the panel is, how do you prepare inquiry-based tasks? Do you start with the old tasks you have, the traditional ones, or do you start them from the scratch? And I'm going to give this question to you, Barbara, first. And Barbara have some slides sent in advance, so I'll show the first. Would you say something before we show the slides?
Yes, let me do that, please, because as always, when I listen to you, John, I am both excited and challenged by what you offer. And I've had the privilege of doing this many times, but I could imagine that for some people listening to you, they think it was wonderful what you're doing, but how on earth do we get started? How do we start to prepare inquiry-based tasks? Well, one of the things that we're doing in Platinum is thinking about different possibilities. And I don't have much time here, but I did bring along 2 possibilities. So if I could have the first slide, please, Thomas. I mean, these 2 are real examples of how we might start to produce an inquiry-based task. So this was an inquiry group of people who teach mathematics in my university, thinking about having these kinds of tasks. And one of the teachers had the question, well, if we work with inquiry-based tasks, what do I put in the exam? Because how do you do inquiry-based tasks in an exam? And so what he did is what you see here. He produced this question. It's a differential equation question. And if you can read that, you can see the first 3 parts are very traditional. But then in the final part, there is just a slightly different way of asking something. So rather than saying find X or evaluate something, the questioning now is there anything special about the solution method if the right-hand side is a different function? And so what he'd done was to just change something very slightly to make that into an example of an inquiry-based task in an exam. And my second example, which I can't make it come, oh, yes. Here is a task that I've actually used myself. It's a calculus task in small groups. Each group choose a differentiable function, not too easy, not too hard, and sketch its graph. Now differentiate the function and sketch the graph of the derivative function. So if the original graph is A and the second graph is B, so if you're given B but not A, how could you generate the graph of A? So that's if you're in a group, that's something to discuss. And then you have a task to exchange your graph B with that of another group. And in that group, your task is to generate the graph A that corresponds to their graph B. And then you can swap back and look at what people have produced. Now, my experience here is that this is a task that very quickly gets students involved. It doesn't require any sophisticated technology, and the students can they do something and they could rapidly talk to each other about what it is and what it means and actually learn from that activity. We ask them to discuss what they learn. So these are only two examples, and in the Platinum Project, we're trying to produce lots and lots of different examples so that people can look at them and think, how might I start to do some inquiry-based work? Of course, what John has shown us is very exciting, but thinking about how we actually start that is really quite challenging.
Thank you, Barbara. It seems like your answer to the question is both yes and no. You have one which started out as a traditional one and expanded, and the other one example is a brand new one created from the beginning. So we're going, yeah, I would like to pose the questions to the other panelists as well. So Andre, you would like to comment on
yes,
how
I raise my hand because I think it's also from strategic point of view wise to start with the small steps that you can do and get some familiarize yourself with inquiry-based tasks, and also for the students to get a bit used to it, because it remains a bit closer to what they are used to. So you gradually drag them more into the inquiry. And the second point I want to make, of course, modification is very basic in our project because we put tasks in our repository, but not with the idea, oh, this is it, and use them, but more like it's giving you an idea that's, and these ideas are expressed in the documents, but also that you can modify them because you have the source material as well, or the tools that have been used for in the tasks. So modification is something which is fundamental also in our idea of, well, inquiry doesn't mean for everyone the same, but you can see what inquiry aspects there are in tasks and see if they would work for your kind of students in your course and make some small changes. And of course, making small changes takes less time. So a teacher who has already a lot of other things on his desk, making a small change, that is something that you can do. And that helps you further before you start thinking about, okay, now I will be more adventurous and start from scratch.
Thank you. Can I send the questions further on, or would you, Marianka, say something about how you designed the task? No. John, please.
Well, my answer is very similar to Barbara's. The answer is both.
Yeah.
Do I modify existing tasks or do you design them from scratch? Because I notice possibilities for tasks when I'm engaged in other things. Perhaps thinking about student confusions or student difficulties. What's the essence that students are missing? Can I display that in some way? And that often leads to a simple task, and then suddenly the task becomes broader and broader and becomes a mathematical investigation. I could actually write a paper about it, but that's not what we're interested in here, of course. Sometimes I notice possibilities when I'm conducting my own investigations. I think, ooh, that was a nice little idea. Nice use of specializing. I wonder if I can create a task that reproduces that for students. So it comes, you notice the possibilities. And I want to underline, underpin, and applaud what Andre just said. Start small. Make small changes. Don't, I was trying to indicate what I've been doing over the last 60 years. Start small and bring the students with you. My experience is that when you make small changes and the students can cope with, then they will start to be attracted to the exploratory. And even I've had people say, can we do more exploring?
Oh, yeah. It's fun. Okay, I think we need to move on. We have limited time and many questions. So the next question we'd like to pose to you is about technology. Let me see if I make the technology work. Oh, that's too fast. When you're designing tasks, do you start with the technology or with the inquiry? Andre.
Yes, well, I always start with the inquiry first, thinking about the inquiry first. because I know the technology well enough. So I think I can focus more on what do I want to do, and I have trust in that I will find a way of doing it, even with the technology. But it depends a bit on the kind of task that you want to do. As I told in the talk, we want to have students working with R and programming in R and working in the RStudio environment. Then I'm first more thinking about how would practitioners do that, and how would I do that if I had given this task, because I was not familiar with R myself when I started the course. And then I'm more thinking about how can I support the students? Can I divide the task maybe in a more doable steps? So then I'm thinking more about the technology than about the inquiry. But then I was triggered by what John was presenting, because then I saw a kind of resemblance with science education, where inquiry comes much in the doing experiments. And when you do experiments, you always advise students first to mess a bit around in the experiment to see what is important, what does make changes in the results of an experiment. And I think that's what John also does when he is a bit tinkering with the tool that he knows about. But then he's a bit messing around with it, with the problem that he is thinking about, and tries things out, and that raises the questions. And like observations and experiments also raise questions, and oh, I should focus on this. And that's, I think, when maybe the technology becomes a bit more first again. So I think it's a bit mixed, whether you want to focus more on inquiry or on the technology side.
Okay, Barbara.
Well, I'd like to say that I would start with neither. I would start with the mathematics. And I was very struck by John's linear algebra animation, because I'm one of these people who have been working with students on change of basis and linear transformations. And knowing how much they struggle with that, I want to find ways of helping them to engage with it in ways that will help them to see through the bits that are causing them difficulty. And certainly, I've been in a situation where we've been with a small group working on the board together and getting lost in the middle of the transformation process. Now, I was thinking, John, as you were using your animation there, what I would quite like to do is make that animation fit a particular problem that somebody has given us as an example to work on, and then work between the animation and the traditional way of working on the problem, so that we're actually using the animation to help us to see what's going on when we do the transformation in the traditional way. So this is something that I could work further on.
Yeah, John, please.
I was using, I have a habit of making animations for presentations so that if I lose confidence about going to the applet, I've got the animation. Of course, the restricting thing about an animation is that it never does what you want to do in the moment, because what it does is something you wanted to do last week or last month or even last year. And so in a live class, I would be using an applet, okay, and I would adjust it so that it was addressing whatever question we were trying to work on, or yeah.
Sorry. I was thinking of a following up question to this about the technology, because if you want the students to use technology, you also need them to learn some technology. And how much attention do you give to developing the students' programming competences to enable them to explore?
Can I say something?
Yeah, you can.
Can I say something immediately? Here's a challenge. Get students to start with sine x and then create the graph of the rotated version of sine x through some given angle which is specified by a slider. That seems to, one of the things that task does is it makes you use transformational geometry, think cosines and cosines, and reveals that you cannot actually express the function that you get, the function corresponding to the rotated graph. You can't express it in simple terms. You can only do it through applying a rotation transformation. So it forces the students to appreciate and comprehend rotations in the context of working with functions. And then you've got this wonderful, I can now create functions that I could never write down before. And that's amazing. It's empowering.
Thank you. But it's also some time spending. I'm not sure, Maria, have you experienced that you need to train the students into software before having them to do inquiry-based tasks?
That's a good question, because we are restricted in time. And last year we had a discussion. I'm giving mainly courses on statistics and probability theory. Where any software is needed. You can't do it just manually. So we had a discussion whether to use R, which really is programming language, or some software which is easy just to click at some buttons. And it was a hard discussion. I didn't sleep 1 week for that because we have courses for 400 students per year, which is different than having just 2 seminar groups with 20 students. So finally, we decided not to go into R because we were especially aware about exam period. Not the semester itself, but to guarantee the environment for the exam in our environment, in this amount of students, we were afraid of that. So I remember the discussion. Finally, we decided to go for the easier software for this 400 students group. But without any software, it's impossible. So I believe that in 21st century, we need some software. It doesn't have to be such a challenging with command line software like programming language. It could be easier software, not only in statistics, in mathematics, also in GeoGebra. But I'm 100% sure that in 21st centuries, all those applets, tools, softwares we have, it would not give sense to work manually like in previous decades. So I really want to encourage those who hesitate if to implement it or not. And I believe also this Corona time helped a lot, because we all are like brainstorming, what can we do, how to engage students through the screens, and how to play more with them, because the interaction is not as easy as it would be in the true room. So I believe that also this development in the area of all these applets, animations, what make easier the study process, it was enhanced through this Corona time. So I believe we will have more opportunities in future, because it's developing fast now. So I believe this is a must these days.
Yeah. So that we have to require sometimes that's what I'm hearing here. And yeah, I'm going to give the first word to Andre and then to Barbara, and we have to be a little bit brief if you can.
Yes, I will.
So we can move on, please.
I will,
Andre and then Barbara afterwards.
Because I showed you that our students in the basic mathematics module, they are programming in R, but that's the first time they do that. They use R already before that. So we thought that, well, they have a little bit of experience, but we have to pay much of attention. So I always spend one of the tutorials is completely on working with R. Then it is still a challenge, because this is the first time that they use such kind of complicated environments for them. They have no programming experience, so we have to pay attention to it. We do that in the lecture and in the tutorial. So I also discuss the use of R in the lectures, but then still the first 2 years, it didn't work well. And we understood that we had to change our materials a bit. And for that purpose, we used our student lecturers because they had their first-hand experience, were close to how students would work with it. And that's how we changed our support for the R programming. And so, yes, we pay much attention to it because we have to.
Yep, thank you. Barbara.
Okay, I just want to draw attention to something that I think is very striking, and that is that as we talk about designing inquiry-based tasks for our students, we are, of course, thinking about working in that central layer of the three-layer model, but we're also working in the second layer. So as we talk about how we go about creating these inquiry-based tasks, we are acting as inquiry teachers. And so being a teacher in an inquiry medium is about thinking in the ways that we've all just been describing and talking about. So perhaps the way to bring inquiry into our work with students is to be inquirers ourselves, inquiring into good ways of approaching the mathematics that we know that students find difficult.
Thank you. I'm moving on to another question here now, and that is about the Google, because if you have seen a task before, I guess some of the point of the inquiry disappear. So how can you make inquiry task Google proof, in meaning that when a student starts searching for ideas, they just find the previous year's students' ideas and not become creative themselves? Do you have any advice how you can? Yes,
I have a comment. I don't have an answer.
Yeah,
I have a comment. I believe that it's a nature of inquiry tasks that they are itself Google proof. I think that it's a nature of it. That traditional way of teaching may lead to questions and answers you can easily Google, but the inquiry-based tasks, they are not easy to Google, and it's a nature of that. And I remember the last semester when we started with examinations online, we got from our university some recommendation for open book exams. And when I was reading that, it was like reading instructions for inquiry tasks. So I was happy that if I had read that 1 year before, I would suppose, oh, these are instructions for inquiry. But now all our colleagues, also those who don't know the term inquiry-based task, they face the challenge how to set their exams in that way that they can't pose questions which are easy to Google. So inquiry-based tasks are Google proof already.
And you got a very thumbs up there, I saw on the from other panelists there. Andre.
Yes, we have two strategies actually to make it Google proof. And for the rest, we don't care, I would say. Yeah. And that's, we ask students when they study mathematical methods and implement them in computer programs, that they generate their own data and explore how the methods work with their own data. So you can't just grab it from somewhere else, because it has to be generated within the program itself. And the second thing is that we use real data coming from research papers. And in these research papers, you see, for example, when they study enzymatic kinetics, that some value on the basis of data is computed for, let's say, the Michaelis-Menten constant. They have to do the same kind of work and explore it and come up with, well, is your answer close to that? Why not? So, and that's also, you cannot Google it because it's not in this paper. Yeah. And for the rest, I don't care, because when they program, it's more like, yes, you look at Google to find some code snippets. How do other people do that? And you use them, but you have to modify them always for your own work. So then it is a more common practice that the practitioners also do. Oh, let's see if someone else has done it before me. We figure out, okay, but then we make it a bit difficult for them to just copy and paste.
Thank you. Makes sense. Yeah, John, would you like to comment on that?
And the only person that a student is hurting when they copy things is themselves.
Of course, but yeah.
In the next course, they will be completely lost if what they've done is copied and pasted in this course. And ultimately, it seems to me that's the best, that's the ethical and the moral and the practical.
Thank you. I have a special question here now for Maria, especially about statistics. So how do you frame inquiry-based tasks to contribute to students' understanding of the big ideas in statistics, such as location, spread, variation, covariation, goodness of fit, etc.? How do you do it in statistics, Maria?
I think this is a big advantage of statistics and partly to probability theory compared to, let's say, algebra or other math theories, because it's very, very close to applications itself. So it's for students easier to understand the context because of the closeness of the applications. So when in this list there are mentions those numerical characteristics like mean or location and dispersion and this sort of stuff. So I think challenging it is especially within lectures, not in seminar groups where they can play with some software simulations, etc. It's easier when they are sitting in front of computers. But when you are in a lecture room with 300 students and you should introduce these concepts without possibility to play with it, which is easier, then I, especially in those introductory courses, use the idea, you are the inventors of these ideas. What would you do if you should represent the column of numbers with some representatives? What would you suggest to do? And they, in fact, develop their own numerical characteristics on their own. And then I can just say, okay, we use it in statistics. And when you adjust it slightly, this is what we call, and in fact, they are in the role of inventors. For instance, when introducing concept of a variance or other statistics, numerical statistics describing variance, then they usually on their own develop something like variance we use in statistics only with absolute values, because it's more natural for them. And then I can say, okay, if you were inventors in 19th century and you didn't have computers for calculating absolute values, then quadratic can also help with the sign. So in fact, I push them to invent these concepts on their own, and then just we adjust it to what we use normally. And in Padlet, I sent a link to Think Theory pages because I really find it brilliant for visualizing concepts in probability theory and statistics, as John Mason did it in algebra or differentiation and mathematical analysis. I don't know many pages or applets where there are possibilities to visualize concepts from probability theory in such a nice way. So I placed it into that Padlet second column.
I have to stop you there, Maria. Thank you.
I know,
so statistics is good for inquiry-based problems. Yuri is already here. We have to thank our panelists once more. Thank you for your contribution. And we are ending the discussion right now. And I'm handing over to you, Yuri. And sorry for stealing one of your minutes.
That's fine. Thank you very much, Thomas. So I will abuse a little bit the time limits in this case. So I basically was asked to make some conclusions and reflections about our webinar. And in particular, I wanted really to see John's reaction. So that's why I asked him to have the screen on so that I can see how he reacts to what I'm saying. This time, I will be talking about my own perception of John's 60 years of teaching mathematics. And I will try to, although I have the logo of Platinum, it's more my personal, say, projection of John Mason's work on my own teaching and also on my own research in mathematics. So trying to connect to John, I was looking into some of his work. And those who didn't have a pleasure to meet him in person, they definitely know his books. So one of those books is Thinking Mathematically, written in co-authorship with Leon Burton and K.S. Stacey. And I was trying to find connections to John there. So the first connection was quite immediate. I found the phrase, watch out for ambiguity. And that was really intriguing. So then I was projecting it onto my own experience. And then I thought, well, what could I connect it with? And then there is another very nice book by William Byers, How Mathematicians Think, where I see ambiguity in the title. And then they have a very nice explanation what is happening. What they say in that book is ambiguity opens up a world that is never boring because it is a world of continual change and creativity. So that is actually the explanation. So we look for stuff which is somehow ambiguous, and we try to connect it to new mathematics. So it's a source for new ideas, for new mathematics. Now, what is the way to go for this? Of course, this is conjecturing. So that same nice book has 312 times conjecture or conjecturing mentioned. So this is the core of exploration. And now what we see here is actually the advice how to go about it. So make a conjecture, however wild. And I really liked it because some conjectures may be very, very rough, but they are helping us to advance. And then you check your conjecture, look into why it is right or wrong. So this is the next necessary step. And then it's something which reminds me a little bit a modeling cycle. So you actually go around conjecturing and reconjecturing for several times. So you make and modify conjectures until you finally come with something you are happy about. So this is the result of your work. And of course, conjecturing is very closely related to inquiry. So this is what John, again, with the collaborators suggests as the ways to improve mathematical thinking. So the plan for improving your thinking has concentrated on these two distinguishable, but nevertheless intertwined factors. The first one is the process of inquiry. The second is emotional states. So this is what we actually experience today. So we were inquiring, but we were also emotionally perturbed. So we saw numbers of participants dropping. We were scared. And this is one of the important things. So emotions play a very, very important role in teaching, both on the side of student, and we feel like how they feel when they don't really know how to approach the problem. But also on our side, say, I consider teaching mathematics as acting, as performing. So I'm an actor in front of my students and I need to engage them in doing math. And this is how I connect again with John perfectly. But here is a very important issue, and I would label it epistemological, because John talks about inquiry, and we in Platinum talk about inquiry. So we need to really take it seriously. And for this particular slide, I even have an epigraph. And this again comes from this lovely book by Byers. A joke is an example of ambiguity and creativity. You have to get a joke. But I'm really serious here. So this is my conjecture about what is Mason's inquiry. So it derives from the old French word "incur." It is deemed, and this is a wild conjecture, to be inspired by the work of Euclid, Euler, Erdős, but to a much larger extent of Clinton Eastwood Jr., whose picture you see there on the top of the slide. And now we talk about the Platinum's inquiry, which is close to my heart. And here I see it differently. Platinum's inquiry derives from irrationality, is based on independent variables, respects invariance, and tends to infinity. Actually, in one of those earlier versions of those slides, I had the word worship. And I've then removed it because I wasn't really sure, but it was already several times featuring in today's discussions. And I think it's not a mistake. It's really something Freudian. It's deliberate. Now, when we come to inquiry in our life as mathematicians and educators, here we have another very nice quote from John Mason, and this is from a different book. It's about researching your own practice and the discipline of noticing. So what John says is that the product of inquiry is not a collection of assertions of uncertain generality, but rather a way of working which may enhance sensitivity to notice, or in other words, educate awareness. So we need to learn how to notice, because noticing is what distinguishes very good mathematicians from good mathematicians and from the rest of the world. And then another important thing is also said by John in that same book. Professional development is a form of personal inquiry in order to broaden and deepen professional sensitivities to notice and to act. Now, I will explain why conjecturing is mentioned more than 300 times in John's book. It's very simple, because conjecturing is very closely related to happiness. And here I use the quote, which is again from Bayer's book. So this is the quote: "In working on a mathematical conjecture, life's ambiguities solidify into a concrete problem. That is, the situation of doing research is isomorphic to some extent with the situation we face in our personal lives. This is one reason that working on mathematics is so satisfying. In resolving the mathematical problem, we, for a while at least, resolve that larger existential problem that is consciously or unconsciously always with us. So by conjecturing and working on conjectures, we actually become happier and we resolve plenty of our problems." And now the final slide, which I have, is about the process of noticing, the process of inquiring. It's something which has no start and no end. Again, I use John Mason's quote. "One of the features of the discipline of noticing is that there are no final answers, only ongoing development and inquiry." And this again triggers something which is very close to me. I have been reasonably reading a lot of Bakhtin's work, and one of those novels or essays was bringing a very, very nice idea to complete this presentation. "There is neither a first nor last word, and there are no limits to the dialogic context. It extends into the boundless past and the boundless future." It was not John Mason. It was neither Platinum that started talking about inquiry. Neither we finished doing this with this webinar. It's ongoing journey and extending into the boundless future. So with those words, I would like to thank you all, especially John Mason, who was really the star today as expected. So we thank you very much for being with us and making this wonderful workshop. We thank both directors, the former and the current directors of Masaryk 2, for leading this discussion. We thank very much the technical team at Masaryk University that really performed impeccable work as usual. We thank all our participants. Numbers dropped, but still those who stayed with us, I hope you enjoyed each and every single moment of this event. And I would like also to remind you that you will get the questionnaire with the answers to this questionnaire. You help us to improve what we are doing. There will be more events we will organize, and we hope to see you soon in one of those. Especially the next one, I think, is planned for June, so we hope to see you there. And in case you forgot why you were here, that's the last slide, which reminds you the title of this webinar. Thank you. Thank you very much for being with us.